Welcome, everybody. I'm very happy to introduce my former teacher, in a way, Professor Dr. Marisa Dalla Chiara. She is a very important person in Italy. She introduced quantum logic, a very important school that now has, since several years, a dependance in Cagliari. And of course, the word of the teachers has widespread to the students. So we are trying to bring the message of this Florence School in the world. So I'm very proud to give the floor to Professor Dr. Marisa Dalla Chiara from the School of Quantum Logic in Florence.
It is a pleasure to meet you here. And it is a great pleasure for me today to participate in this interesting quantum afternoon and in such a beautiful scientific environment that is very inspiring for new ideas in transdisciplinary research. So I would like to thank all the organizers for this very, very beautiful and inspiring seminar. So my talk is actually a joint paper with Roberto Giuntini, who is very well known in this environment, and Giuseppe Sergioli. Quantum computation and quantum information theories have recently inspired the development of new forms of quantum logic that have been called quantum computational logics. And these logics are completely different from the historical quantum logic that had been proposed by Birkhoff and von Neumann in the famous article, The Logic of Quantum Mechanics. In quantum computational logics, meanings of formulas are represented as pieces of quantum information. So quantum states living in different Hilbert spaces whose dimension depends on the linguistic complexity of the formulas under consideration. And logical connectives are interpreted as particular quantum logical gates that are unitary operators that describe possible time evolutions of the quantum systems that store the information in question. Let me very briefly recall some basic notions of quantum information that play an important role in quantum computational logic. In quantum computational logics, because we have different forms of quantum computational logics. We don't have a unique quantum logic so far. As is well known, the mathematical stage where any piece of quantum information is usually but not always supposed to live is a finite dimensional Hilbert space whose general form is the following. So an n-fold tensor product of the Hilbert space C2. I will indicate this particular n-fold tensor product by Hn, and I will also call this space simply the n space. An n space can be regarded as the Hilbert space associated to composite quantum systems consisting of n parts. And the number n depends on the complexity of the information stored by the quantum systems in question. As is well known, the canonical basis of the space H1, that is the space C2, consists of the two following unit vectors, the vector ket0 and the vector ket1. In the general case, the canonical basis of a space Hn consists of all vectors that have the following form, usually indicated in this way. This is the n-fold tensor product of vectors that are either the vector ket0 or the vector ket1. I will use here the following terminology. In this terminology, a Q register is a unit vector of an n space. A qubit or qubit state is a Q register of the space C2. A register is an element of the canonical basis of a space Hn, and finally, a bit is a register of the space C2. Q registers are pure states, representing maximal pieces of information about the quantum systems under investigation. Maximal pieces of information in the sense that they cannot be consistently extended to a richer knowledge. But generally, a piece of quantum information may also correspond to a non-maximal information. So a mixture, mathematically represented as a density operator law of an n space. And of course, any Q register psi corresponds to a special case of a mixture. The projection that I indicate in this way, P psi, that projects over the closed subspace determined by the vector psi. Any Q register psi of an n space can be represented as a superposition of registers, as is well known, in the following way. And according to the standard interpretation of quantum superpositions, a Q register can be also regarded as a kind of cloud of possibilities. In the following sense, the uncertain information psi might be transformed into the certain information corresponding to this register with probability value equal to this number. And these virtual possibilities are in a sense all coexistent. As is well known, this strange coexistence is one of the peculiar features of the quantum theoretic formalism, very strange from a classical point of view. From an intuitive point of view, sometimes one refers to some metaphors in order to illustrate this strange coexistence from an intuitive point of view. A well-known, funny metaphor is the metaphor of the quantum skier who is able to run at the same time at the left and at the right part of a given tree. As happens in classical information theory, the two bits ket1 and ket0 can be also regarded as the two classical truth value 1 and 0. And in this way, any qubit that has its canonical form, this canonical form, can be logically interpreted in the following way. The qubit psi represents a generally uncertain piece of information that might be true with probability equal to this number and might be false with probability equal to this other number. And on this basis, we can now consider two special quantum properties represented by two special projections of the space H1. The projection that I indicate by P11 that projects over the closed subspace determined by the vector, the ket1, the bit 1. And the projection that I indicate by P10 that projects over the closed subspace determined by the vector ket0. And from an intuitive point of view, it seems natural to assume that these two projections represent respectively the truth and the falsity for the space H1. And this definition can be then generalized to any space Hn. So I will indicate by Pn1 the truth property of the space Hn, and by Pn0 the falsity property of the same space. There is no time to give the precise definition. And now we can apply the Born rule. So we can define a special quantum probability function that I will indicate by P, that assigns to any piece of quantum information ρ a value in the 0-1 interval. So this is the definition. For any density operator ρ of an n space, P of ρ is defined as the trace of the operator ρ Pn1, where this operator, as we have seen, represents the truth in our framework. So from an intuitive point of view, this number, the number P ρ, represents the probability that the piece of quantum information ρ is true. And we will see how this number will play a very important role in our quantum computational semantics. As is well known, and it has been mentioned also today in this meeting, quantum information is processed by quantum logical gates. Let me say simply gates. Gates are special examples of unitary operators that transform in a reversible way the pure states of the quantum systems that store the information in question. And then all gates can be extended also to mixtures in a canonical way. As is well known, every computation that might be performed by a quantum computer, either a theoretic computer or a real computer, is mathematically described by a quantum circuit that is a finite sequence of gates having this form, and all these gates are defined on a particular quantum computational space, Hn. I consider here for logical aims only four gates that have a special logical interest. And for simplicity, I will refer to the smallest spaces where these gates can be defined. And then all gates can be generalized to higher dimensional spaces. The first gate that I will consider is the gate negation, defined on the space H1, the space C2, and the gate negation, indicated by not, is the linear operator that transforms the bit get 0 into the bit get 1, and vice versa. So this happens in classical semantics. The quantum negation transforms the truth value falsity into the truth value truth, and vice versa. Another very important gate that has been mentioned by Roberto before is the gate XOR that is defined on the space H2. XOR is often defined as a controlled negation. But for logical aims, it is more natural to represent this gate as a reversible disjunction, the disjunction out in Latin. I don't know whether in German out corresponds to entweder oder perhaps entweder oder has a different. Entweder oder is the right translation of out. And in Italian, we don't have a good translation of out. So XOR is out, entweder oder. And this is the definition of XOR. XOR applied to the register XY transforms this register into the register X1 when X and Y are different, and into the register X0 otherwise. So XOR leaves unchanged the first bit X, while the second bit Y is transformed into the truth value of the classical exclusive disjunction between the two bits X and Y. And then we have the Toffoli gate. Toffoli is defined on the space H3, so it is a ternary gate. Toffoli is very interesting from a logical point of view because, as I have said, Toffoli allows us to define a reversible conjunction. Anyway, at least as far as I know, because I am not at all an expert of technological problems concerning quantum computers. But as far as I know, Toffoli is a somewhat inconvenient gate for the technology of real quantum computers, just because Toffoli is a ternary gate. Anyway, yes, this is the definition of Toffoli, but today I don't illustrate this precise definition for lack of time, and also because, in fact, I will never use the Toffoli gate in the examples that I am going to consider today. The negation, the control negation, and the Toffoli gate are all examples of semi-classical gates. Why semi-classical? Because they are unable to create superpositions from register inputs. But of course, quantum computer theory cannot help using also genuine quantum gates that can transform classical inputs, registers, into genuine superpositions. And an important, a very well-known example of a gate that is genuine quantum is the Hadamard gate that is defined on the space H1, on the space C2, and this is the definition. Hadamard transforms both bits ket0 and ket1 into two genuine superpositions, this superposition and this superposition, two different superpositions. Thus, the Hadamard gate transforms both bits into two distinct genuine superpositions that might be either true or false with probability 1/2. And this is a very important gate, I guess, also for real quantum computers. It's very, as far as I know, it is very frequently used. The Hadamard gate, which cannot have any counterpart in classical computation, where superpositions do not exist. This gate plays a very important role in quantum computation. Why? Because creating superpositions means creating parallel structures. A very interesting example where the Hadamard gate plays an important role is a particular quantum circuit that creates entanglement. And this circuit, that is very well known, is usually called a Bell circuit because when applied to the input represented by the register 00, the output of our circuit is one of the Bell states. So this is a particular example of a Bell circuit that consists of 3 gates, all defined on the space H2. The first gate is XOR. the second gate is not of the space H1 times the identity of the space H1. And the third gate is Hadamard of the space H1 times the identity of the same space. So if we no, something is missing. No, everything is okay, sorry. If we now apply this Bell circuit to the input represented by the register cat00, we obtain as the output the following genuine superposition. The superposition of the register cat00 and the register cat11 and the register cat00. So since I will not consider here other examples of Bell states, I will indicate this particular superposition in the following way, cat Bell, and I will call this state simply the Bell state. The Bell state, as is well known, is a typical entangled state, a pure state of a composite two-particle system which determines the states of its parts that cannot be pure. So by using the notion of reduced state, we can represent the states of the two parts in the following way. So the states of both parts turn out to be the same proper mixture, the mixture one half of the identity. So what happens here? And this will be very important for our quantum computational semantics. The information about the whole is more precise than the information about the parts and cannot be represented as a function of the pieces of information about the parts. So we have that the information goes from the whole to the parts and not the other way around. Against a basic principle, both of classical physics and of classical logic. And this principle is usually called the compositionality principle. And now, finally, we can turn to our quantum computational semantics. But in order to have a semantics, we need, of course, a language. And in the literature, different forms of quantum computational languages have been considered. For simplicity, I will refer today to the simplest form of quantum computational language. An example of a sentential language, let me call this language L, that contains atomic formulas, including two special formulas indicated by T and F that denote the truth and the falsity respectively. And then the following logical connectives: a connective negation corresponding to the gate negation, the exclusive disjunction indicated in this way, so out, corresponding to the gate XOR, the Toffoli connective T corresponding to the Toffoli gate, which allows us to define the reversible conjunction indicated in the usual way, and finally, the Hadamard connective that I indicate in this way, corresponding to the Hadamard gate. So these connectives simulate at a syntactical level the behavior of the corresponding gates. And we obtain in this way an appropriate logical language for the description of quantum circuits. For instance, our Bell circuit will be described by this formula that I indicate by beta Bell, the exclusive disjunction between the negation of the Hadamard connective applied to the false formula and the false formula itself. There is Yes. Of course, we have the natural correspondence between the Bell circuit and our Bell formula. A syntactical notion that will play a very important semantic role is the concept of atomic complexity of a formula alpha. What is the atomic complexity of alpha? It is simply the number of occurrences of atomic formulas in alpha. For instance, the atomic complexity of our Bell formula, this is our Bell formula, is the number 2, because we have here 2 occurrences of the atomic formula F, the falsity. The atomic complexity of a formula alpha is semantically very important. Why? Because it determines the semantic space that I denote by H alpha, where any piece of quantum information representing a possible meaning of alpha shall live. So this is the definition. Suppose that our formula has n atomic occurrences. We say that the semantic space of alpha is just the n space. This is a very naive, innocent syntactical notion, but it is important because it determines a bridge from the syntactical world to the Hilbert space world. And this bridge will be very important for our quantum computational semantics. Another important syntactical notion that will play an important semantic notion is the notion of syntactical tree of a given formula alpha. What is the syntactical tree of alpha? In fact, any formula alpha can be decomposed into its parts, giving rise to a syntactical configuration that we call just the syntactical tree of alpha. The best thing is to look at a particular example. Let us consider again our Bell formula. You remember, this is the Bell formula. What is the syntactical tree of the Bell formula? It is a sequence of levels where any level is a sequence of subformulas of alpha. The first level, level 1, is the sequence that contains the formula itself, so in our case, the Bell formula. The top level is the sequence that contains the occurrences of the atomic subformulas of our formula. And then level I plus 1 is obtained by dropping the principal connective in all molecular formulas occurring at level I, and by repeating all atomic formulas that occur at level I. So you see here at level 2, we have dropped the principal connective that was the exclusive disjunction. At level 3, we have dropped the negation. And finally, at the top level, we have dropped Adamart, and so we have obtained the sequence that contains the 2 occurrences of the formula falsity. The syntactical tree of any formula alpha uniquely determines a quantum circuit. That is a sequence of gates all defined on the semantic space of alpha. And such sequence, for obvious reasons, is called the quantum circuit of our formula alpha. The best thing is to look again at a particular example. Let us consider again our Bell formula. Of course, as expected, the quantum circuit of the Bell formula will be the quantum circuit. And this is not a formal definition, but I could easily give the general formal definition because, as expected, this procedure can be applied to any formula alpha. And now, finally, we can introduce the basic concepts of our quantum computational semantics. I will consider a holistic and contextual version of the quantum computational semantics, where the characteristic holistic features of the quantum theoretic formalism play an essential role. As happens in any semantics, the basic concept is the concept of model. And here we consider a notion of model that is holistic. So we speak of holistic model of our language L. The concept of holistic model is based on a weaker notion, the notion of holistic map. What is a holistic map? A holistic map that I indicate by whole is a map that assigns to each level of the syntactical tree of any formula alpha a global meaning, represented by a density operator living in the semantic space of alpha. On this basis, the meaning that the map whole assigns to alpha is identified with the meaning that whole assigns to the bottom level of the syntactical tree of alpha. In this way, whole alpha is whole of level 1 of alpha. Given a formula alpha, any holistic map whole determines the contextual meaning with respect to the context whole alpha. Whole alpha is the meaning that whole has assigned to our formula alpha. So the contextual meaning with respect to the context whole alpha of any occurrence of a subformula beta in alpha. For instance, suppose that the subformula beta, occurs in alpha at the ith level at the jth position of this level. So I indicate this particular occurrence with the notation beta ij. What will be the contextual meaning of this particular occurrence, beta ij, with respect to the context whole alpha that represent the meaning of alpha? This contextual meaning can be naturally defined by using the notion, the quantum notion of reduced state in the following way. So what is this? This is the state of the jth subsystem of the system that is in the state assigned by whole to the ith level of the syntactical tree of alpha. So it is a very natural definition from a quantum theoretic point of view. And now the concept of holistic model of our language L can be defined as a holistic map that satisfies some natural logical restrictions. The first restriction is the following condition. The map whole shall preserve the logical form of any formula alpha. In other words, the meaning of each level I, of the syntactical tree of alpha, different from the top level, shall be obtained by applying the corresponding gate of the quantum circuit of alpha to the meaning of the level that occurs immediately before. So this is the condition. Second condition, whole shall assign the same contextual meaning to different occurrences in the syntactical tree of alpha of one and the same subformula beta of alpha. And this unique contextual meaning will be indicated in the following way as whole alpha of beta. The intuitive idea is that the contextual meaning shall not change in the framework of one and the same formula. Third condition, the contextual meaning assigned by whole to the true formula and to the false formula shall be the right one, so the truth and the falsity. The characteristic holistic features of our model's whole are due to the fact that any whole assigns to any formula alpha a global meaning that determines the contextual meanings of its subformulas. So generally, the meaning of the whole determines the meanings of its parts and not the other way around, against, again, the compositionality principle. Notice that the meaning whole alpha, the meaning that whole has assigned to the formula alpha, represent a kind of autonomous semantic context that is not necessarily correlated with the meanings of other formulas. One and the same formula may receive different contextual meanings in different contexts, as in fact happens in the case of our normal use of natural languages. And now we can define the basic concepts of any semantics, the concepts of truth and of logical consequence. We say that the formula alpha is true in a model whole when the probability of the meaning that whole has assigned to alpha is 1. And we say that beta is a logical consequence of alpha when for any formula gamma, such that alpha and beta are subformulas of gamma, and for any model whole, the probability of the contextual meaning of alpha with respect to the meaning whole gamma is less than or equal to the probability of the contextual meaning of beta with respect to the same context. Notice that here, both concepts, the concept of truth and the concept of logical consequence, are probabilistic concepts. And probability here means quantum probability that has been defined in terms of the Born rule. So now we have a concept of logical consequence, and as always happens in logic, a concept of logical consequence immediately determines a logic. So in our case, we call holistic quantum computational logic the logic that is semantically characterized by this particular concept of logical consequence. What kind of logic is this logic? One is dealing with a very weak form of logic, where many important logical arguments that are valid not only in classical logic, but also in Birkhoff and von Neumann's quantum logic, turn out to be violated. For instance, in this logic, conjunctions is generally non-idempotent, non-commutative, non-associative. Of course, this holistic semantics does not forbid situations that may be compositional or context-independent. And interestingly enough, classical semantics can be described as a special case of quantum computational semantics, in the same way as classical computation can be described as a special case of quantum computation. And finally, let me refer to some possible applications. Quantum computational logics can be naturally applied to a formal analysis of semantic phenomena where a relevant role is played by holism, contextuality, vagueness and ambiguity, allusions and metaphors, coexistence of alternative, possibly contradictory ideas. Let me very sketch to some possible examples. For instance, the semantics of natural languages, which is essentially holistic and contextual. We need only think how children learn their mother language, showing an extraordinary capacity of understanding and using correctly the contextual meanings of expressions that occur in different contexts. And it often happens, we have many examples of this kind, and it often happens that the meaning of a global expression is grasped and used in a clear and correct way, while the meanings of its parts appear more vague and ambiguous, just as happens in the quantum theoretic formalism. Another example is a formal analysis of literary languages, especially of poetry, where allusions and metaphors play an essential role. One can also study the possibility of a quantum musical semantics, where musical ideas can be represented as quantum-like superpositions. In this framework, one can formally describe the ambiguities that characterize musical languages, and it is very well known that ambiguity is an important characteristic feature of music. And furthermore, extra-musical meanings which are evoked by music can be dealt with as example of vague possible words where events are generally indeterminate, as happens in the case of quantum objects. With Roberto, we have studied in some papers these very special and peculiar quantum musical semantics, and especially in this book that has been written in collaboration with a musicologist, Eleonora Negri, and with a composer, Riccardo Luciani. Finally, let me refer to problems that concerns recognitions of concepts and also of musical themes. These problems can be successfully investigated in the framework of a quantum-inspired approach to pattern recognition and to machine learning. And in this framework, the intuitive concept of Gestalt, which plays a very important role in human recognition, as shown by the famous Gestalt approach to psychology. So this intuitive concept of Gestalt can be adequately simulated by convenient mathematical notions of the quantum theoretic formalism. But this is a longer story that cannot be told now, perhaps in different occasions. And so I will stop here, and these are some references that are connected with the problems that I have discussed in my talk. So thank you very much for your attention.